All right, in this set of notes, we are going to look at length contraction. You can see that our chart is kind of set up similar to the mass chart, where our velocities are given as a percent of the speed of light. But let's go off to the side for a minute and let's start with the length equation, the length contraction equation. So it's supposed to be a lowercase l, but my lowercase l's look like ones, so I'm going to use a capital L. So this is the length. This is the original length as viewed in the spaceship. And this time, instead of dividing by that big mess, we are going to multiply by the big mess. So 1 minus v squared over c squared. Okay, so v, again, is going to be the velocity of the spaceship. L0 is going to be length of the object inside the spaceship, length inside spaceship. And L is going to be the length viewed from Earth. Okay, so let's do an example and see what happens to length when something goes really, really fast. All right, so how about for our example, let's do 0.98 c. All right, so let's figure out first of all how fast our spaceship is going to be going. So 0.98 times 3e8. Our spaceship's going to be going 2.94 times 10 to the 8th. So I'm going to write that down. 2.94 times 10 to the 8th. Again, I don't really care what that is in miles per hour. All right, so how about we use as an example a meter stick? Because the length of a meter stick is 1 meter. So the length of the object that we're going to put in the spaceship is 1 meter. And so now this meter stick is inside the spaceship and it's going to be going really fast, 98% of the speed of light. And what is the length of the meter stick when we look at it from Earth? So let's number crunch that. So we have our velocity there. So I'm going to square that velocity. I'm going to divide by 3 times 10 to the 8th squared. I'm going to say 1 minus that answer. Then I'm going to have to square root that answer. And then I would have to multiply by L naught, which is 1. That's the length of the meter stick, so I'll just do it for fun, times 1. And so how long is the meter stick going to look from Earth? 0.19 around, we'll call it 0.2. We'll call it 0.2. All right, 0.2. So if I talked in terms of centimeters, the meter stick is 100 centimeters, and 0.2 meters is 20 centimeters. And you can see that the meter stick contracted. The meter stick shortened. That's what length contraction is. When something goes super, super fast, it gets shorter. It truly gets shorter. It gets shorter viewed from Earth, but the meter stick really didn't get shorter in the spaceship. So let's change our story now to a person. All right, so you get in the spaceship. And let's pretend that you are, I'll just make up a number. So we'll take a person here. And let's pretend that you are 6 feet tall. And we're going to send you super, super fast. You're in the spaceship going super, super fast. Your length does not change. You still look and are 6 feet tall. But when I look at you from Earth, I say, oh my God, look at that little tiny short person that I see out there in the spaceship. And you might appear to be 2 feet tall, from my perspective. From your perspective, in the spaceship, it hasn't changed. In fact, when you're in your spaceship, you look at me and you say, oh, look at that little tiny short person on Earth. I appear to be contracted to you, and you appear to be contracted to me. Because the point is, we are calling this the spaceship. I call it the SS, the spaceship. And I'm calling this the Earth. But really, the spaceship could be this guy's planet. So maybe his is planet X. And maybe the Earth looks like a spaceship to him. So again, it's that cyclical story that we never know whose perspective is right. So therefore, both perspectives are right. All you need to take away is that when something goes super, super fast near the speed of light, it will be shorter. It will look shorter. All right, let me add one last piece to this. So what if I'm not talking about the meter stick and I'm not talking about you? I'm literally just talking about the spaceship itself. So let me see if I can draw a good spaceship here. Sometimes it's hard to draw a spaceship. All right, so let's see. And every time I draw a spaceship, people start to giggle. So don't giggle, all right, in my spaceship, because I know what you're thinking. That's why I always write the word NASA down here to remind you it's a spaceship. And I like to have windows in my spaceship like this. Windows. Then it looks more like a spaceship. All right, so now let's add on something to length contraction. There's a technicality here. Length only contracts in the direction that it's moving. So I'm going to tell you right now that my rocket ship is moving in this direction. It's like flying straight up. So when I look at that rocket ship from Earth, so here I am down here on Earth, and I look up at this rocket ship, it is going to contract, it's going to shrink in the direction of motion, so it's going to contract like this. So what would a contracted spaceship look like? Let me see if I can draw a contracted spaceship. You see I kind of like just squished them, squish. And I'll pretend I can't really read those NASA words. But look at his windows. Here's his windows. So this is got the windows. Do you know what that looks like? Some people would say it looks like a flying saucer. Do you know that people predicted, or people said that they saw flying saucers, and they described what the flying saucer looked like long before Einstein predicted length contraction and explained what a contracted rocket ship might look like? People said they saw flying saucers, they described what they looked like, and then years later Einstein comes up with this prediction. So yeah, well that totally makes sense. You might have seen a rocket ship flying in the air near the speed of light, and it would have looked like that to you. So I'm not saying that I believe in UFOs. I don't know if I believe in UFOs, but I do believe that there is life out in the universe, some form of life. And it could be that some form of life is more civilized than us, more intelligent than us, and they have learned how to go fast. And they have learned how to go fast, and maybe they've flown out there and they are looking contracted like this. What if the rocket ship flew sideways? That'd be kind of weird, to go like this. But if it flew sideways, what would it look like? Let's draw a sideways contracted rocket ship. So it's going to have to squish like this. So it's going to have the same height, but it's going to be super squished. So I'll draw it like this. How high is it like this? Not a very good drawing, but it could look like a pencil, like pencil thin if it's contracted in that direction. So 2 takeaways from this lesson. When something goes super, super fast, approaching the speed of light, the length contracts, but it only contracts in the direction that is traveling. And we will limit our discussion to flying straight up or flying sideways, and we'll never fly at an angle because that'll just be too much to handle. Okay. As before, pick 5 values on the chart. We did one together, so pick for more, and that's all you have to do on that chart. Okay?